Welcome to lecture number 2 in ECE 761 Robotics, Rotation Matrices. Now in a robot, you've got typically joints connected with their powered by a motor, connected to other links. Like I want to go from the shoulder to the elbow to the wrist. As the joints move or rotate, the location of the subsequent reference frame, shoulder, elbow, wrist, depends upon the current reference frame and the angle. To figure out where these reference frames are, I need a rotation matrix, such as the reference frame on my elbow is going to rotate as I turn my shoulder around. When you have a rotation matrix, I can rotate it by the x-axis, y-axis, or z-axis, so we'll have 3 different types of rotation matrices we'll be looking at. Point is defined by 4 coordinates. That's your x, y, z coordinate, along with a scalar. In this class, the scalar is always 1. You can use that for animation. If I make that number bigger, it blows up. If it becomes smaller, it goes away, gets smaller. So this is kind of like the scaling for animation. We'll be just using it as 1, and I've got my x, y, z coordinate. Basically, where's my shoulder relative to the earth frame? If I have a rotation matrix, I want to find out where is another point as I rotate it. So to go from one reference frame to another, I have a transformation matrix. That's the T10. And the notation is T10 takes you from reference frame 0 to reference frame 1. If I have an XYZ axis, this is the Earth reference frame X0, Y0, Z0, and I rotate about X0 in the clockwise direction. That's put your thumb along the X-axis, your right thumb, and the direction the finger curl is the positive direction. A point in reference frame 1 relative to reference frame 0 will look like this. The x-coordinate doesn't change. That's the 1, 0, 0. The y-coordinate, however, if I have a point right here in y0, in y1, it'll be cosine of the angle. The z-coordinate is going to be negative. It's below the z-axis. That's over here, the minus z. The z-coordinate, if I start over here, if I rotate at a small angle, it becomes a cosine of the angle. That's this guy. The y-coordinate is now in the positive direction, the plus cosine or plus sine theta. So this is a rotation matrix about the x-axis. About the y-axis, again, I start in reference frame 0, the black reference frame, rotated by theta. Y0 stays the same. That's this number here. The x-coordinate changes by cosine on the x-axis and sine, and the z becomes cosine minus sine. Likewise, if I rotate about the z-axis, the z stays the same. X and y become cosine, and the opposite diagonal is sine minus sine. So that's the rotation matrix. What you can do with that is, suppose I have a point relative to reference frame 0 at 1, 2, 3. Where's that point if I rotate 90 degrees about the x-axis, y-axis, and z-axis? And here I misspelled x, y, z. So starting out, for convenience, let's just have c be the cosine of 90 degrees, s be the sine of 90 degrees. This is the rotation matrix about the x-axis, y-axis, and z-axis. Same equations we had before. Here's my point relative to frame 0. Now the point relative to frame 1 will be this rotation matrix. That's the transformation from 0 to 1 times your point. So if we rotate about the x-axis, here's the new point. 1, 3, minus 2. Rotate about the y-axis, becomes minus 3, 2, 1. Z-axis, 2, minus 1, 3. So it's the same point, but if we rotate the axis, its location relative to that new axis is moved. Second example, I can rotate about the x-axis and y-axis. To do that, I do that in 2 steps. If I first rotate about the y-axis by 20 degrees, then rotate about the z-axis by 30 degrees, what I'll do, this is a rotate y. So I'm going to take the initial point, rotate it about the y-axis by 20 degrees. That's point 1. Now take point 1, rotate about the z-axis by 30 degrees, gives you point 2. And notice with the symbolism, P0 times T10 gives you P1. P1 times 221 gives you P2. And I can also simplify this and say T21 times T10 gives you T10. Takes it from reference frame 0 to reference frame 2. In MATLAB, the way I would do that is let's define cosine and sine to be cosine and sine of 20 degrees. Do the same matrices. That's T10. Now take it at 30 degrees. That's T21. Now here's point 0, point 1, point 2. And what I get is point 0, point 1, and point 2. There's the point relative to reference frame 2. The homework for this week looks at this type of problem. The whole goal is to convince you that rotation matrices really work. So let's just take a shape. On the lecture notes, I'm going to use an arrow. I'm going to define an arrow with 8 points. You basically go around this curve and draw the points, draw the arrow. That'll be in the YZ plane. I now want to sit there and rotate that arrow using the rotation matrices. So first, if I just take that XYZ, define it, and then here's a display routine in MATLAB. It's linked on Bison Academy. Display that with the identity matrix. And that's what it looks like. This is the x-axis. I'm looking right down it, so I can't really see it. That's just a point. Here's the y-axis. There's the z-axis. There's my arrow in the YZ plane. It's a little bit easier seeing it with orthographic projection. So by changing my display routine, I'm now going to display, rotate about the y-axis by 45 degrees, rotate about the z-axis by 45 degrees. There's my display rotation matrix. In my display routine, let's get this out of the way. When I display the point, this is displaying the point with that transformation. This is how I look at it. If I look at it 45 degrees over y, 45 degrees over z, that's my orthographic projection. It's a little bit easier to see what's going on. Now let's do some rotation matrices. Suppose I have a 2-degree rotation right here, cosine of 2 degrees, sine of 2 degrees. My 3 rotation matrices rotate about the x, y, z axis. Let's rotate by 2 degrees and repeat over and over again. Let's do that for 180 steps, which will be 360 degrees. I'm going to take my initial point, my rotation matrix, rotate it by 2 degrees over and over again. What happens, oops, is I forgot to delete some of the code. What happens is the green line is the x-axis. I'm now rotating about the x-axis 2 degrees every step. That's rotation about the x-axis. If I want to rotate about the y-axis, let's get rid of that pause. Now instead, let's make this the rotate y. Rotate about the y-axis by 2 degrees each step. That takes this guy, the red line is the y-axis. I'm now rotating the arrow about the y-axis. Think of that like a robot joint. I'm taking that shoulder and rotating it. If I then replace that with a z, rotate about the z-axis, and there you have it rotating. I can then put that into a sequence. I'm going to first rotate about the x-axis, then rotate about the y-axis, rotate about the z-axis. And notice this is a script. I'm just taking the section of code and running it. It's a lot easier than typing it in by hand over and over again. I first start rotating about the x-axis, 360 degrees. Now I rotate about the y-axis. Then rotate about the z-axis. That's what rotation matrices do for you. The homework for today is to convince yourself that rotation matrices really work. The homework is pick a shape other than the arrow. Anything else, take your initials, Star Trek symbol, whatever you like. Define the points for it, and then rotate about the x-axis, y-axis, and z-axis. The goal being to convince yourself that the rotation matrices really do work. I can take a point and move it with the rotation matrix. That'll be useful later on for robotics when I have a shoulder joint that's rotating. Homework set number 2 is basically trying to convince you that rotation matrices really do work. So it's pick a shape other than an arrow, specify the XYZ coordinates of it, and get it to draw on the screen. Now rotate that object about the x-axis, y-axis, and z-axis, the same way I did that with the arrow, and demonstrate that your code works. You can use the YouTube video, screen capture, share your screen on Zoom, however you want to submit your homework. The main goal is convince yourself that rotation matrices really do work. For now, let's just get the rotation matrices working.